So we shall start the class fuels, where we are going to discuss on the use of coke in metallurgical process and describe coal gasification technique and also discuss the refining of petroleum and cracking methods. We have huge metallurgical industries across India as well as across world, producing various metals from ores. So here we require a fuel. For that, major of the fuel is provided with coke. Okay? The solid fuel coke is used. Nearly 90% of the total metallurgical coke production is dedicated to blast furnace operations. Metallurgical coke, along with iron ore and limestone, is layered into the blast furnace to convert iron ore into metallic iron. Coke is having majority of carbon as its major composition, and it reacts with the blast air to produce carbon monoxide, which in turn reacts with iron oxide to produce carbon dioxide and metallic iron. A good coke is used in metallurgical process should possess the following requisites. First one, it should have good purity. That means it should possess less moisture. If moisture is more, the calorific value will be low. Ash also should be less. If again more ash is there, it will reduce the flow of heat. Combustion velocity will be reduced, and also calorific value will be lowered. Also, the coke should have lower sulfur content and phosphorus contents. Otherwise, these sulfur and phosphor, even nitrogen, will get converted to their respective oxides, causing a pollution problem. So, if moisture is present, more moisture is present, it will reduce the calorific value. Strength of coke should be good, so that we can produce compact coke. The hard and strong coke blocks or seams are used in the metallurgical process. Why hard and strong compact cokes are required is they should withstand the pressure of overlying solids. When you mix this ore, flax and coke, this coke should withstand the weight of ore and flux so that it won't collapse. Okay, that is why compact and hard and strong coke is required. Porosity of the coke should be good, so that it will allow the oxygen to interact with carbon in a better way for complete combustion. So if porosity is more, oxygen can penetrate in through the pores to interact better with carbon molecules and complete combustion occurs. Usually, metallurgical coke, size, medium-sized metallurgical coke is used. Not bigger-sized blocks or even small-sized blocks are not used. Small-size coke, if you used. Rate of combustion should be lower, so the calorific intensity, hence the quality of fuel is better. Of course, the coke should be economical and its calorific value should be high enough. So these are the features of a good quality coke. How do we produce coke? So this metallurgical coke is produced by destructive distillation of coal in coke ovens. Usually these coke ovens will have three chambers. One is coking chamber, heating chamber and regenerative chamber. And each of these chambers will hold nearly 10 to 35 tons of the coal. So that much bigger size chambers will be there. So all of the chambers are lined with refractory because it has to be handled with very high heat. So refractory bricks are used. Coking chamber has ports in the top of for charging the coal, and the manufacturing includes preparing, charging, and heating of the coal, removing and cooling of the coke product, cooling and cleaning and recycling the oven gas. The byproducts obtained after coke product or oven gas that is again reused in other form. Coke oven gas is formed by heating coal to 1100 degrees centigrade without the access of air. So what is the composition of coke? Usually it will have somewhere around 50% of hydrogen, somewhere 35% of methane, and carbon monoxide approximately around 10%, ethylene approximately 5%. The composition may also include a small quantity of benzene, ammonia, hydrogen sulfide. Uh, Coal is heated in oxygen-free atmosphere until all volatile components in the coal are evaporated. So once all these volatiles are evaporated, what we get is the coke. Okay, so it's a typical representation of coke making is like this, where the coal is driven into the screw loader, where this screw turns or rotates and carry forward the coal into the heating chamber. So this is a tubular dryer where now the moisture is removed and then it is drawn into the cyclone. So here the gases produced are taken off and the powdered coal is conveyed through the belt conveyor into the firing oven. Okay. When we put here, so we get coke here. Okay, so all volatiles get escaped in these vents, and you get coke at the bottom. Okay, so they will be compacted into the required size and then sent to the industries. Okay, coal gasification is done for producing synthetic gas or syngas, which is a mixture of majorly carbon monoxide and hydrogen. CO plus H2 is syngas. Okay, small components composition of CO2 and CH4 water vapor also will be there when we go for coal gasification. Um, this is underground coal gasification and over the earth surface coal gasification is also done. What generally they do is in the injection well, coal will be here. Through the injection well, steam is sent here along with the oxygen. So in the production well, what happens is the heated coal will take up this steam and oxygen, and you get different gases here. Okay, so obviously when we carry out this reaction at a depth of nearly 1000 meters, high pressure will be there. So what happens? It will react to yield different gases having major composition of carbon monoxide and H2, and in small quantities other gases. So CO2 produced can be captured, it is sequestered, and further it can be used for various purposes. And this hydrogen and carbon monoxide are treated with nitrogen, and ammonia can be taken off. So air separation plant will provide the nitrogen here, and nitrogen reacts to give ammonia. Okay. So this process we call it as a continuous retraction injection point process, where coal gasification is carried out. Depending on the porosity, hardness of the coal seams, that is small blocks, the pressure and temperature would be varied to get. Okay, because this size of coal hardness matters in producing the syngas or synthetic gas. Optimal pressure promotes groundwater flow into the cavity, thus confining the chemical process to the limits of gasification zone and preventing contamination in the area. But now, suppose if we increase the pressure, what happens is the gases produced will be lost. Okay, that problem arises if we increase the pressure. If the coal in deep seams is surrounded by impermeable overburden, a reasonable balance of pressure and gas loss is balanced. That can be accomplished by balancing gas pressure in the injection valve and the production valve. Ideal temperatures in the above ground coal gasification are about 1000 degree centigrade. However, it may or may not be possible to achieve this temperature in underground coal gasification. That means underground coal gasification, the pressure will be very high, hence the temperature also can be reduced while achieving the yield of required yield of coal gasification. So I said crude oil or petroleum is one of the natural resource. As such, petrol is of not of much use. So what we do is we convert this petroleum or crude oil into various fractions that will be of a good use. Okay, crude oil from the field is a viscous dark colored liquid containing a lot of impurities. Impurities include sand, brine, etc. It has unpleasant smell. That is because of the sulfur compounds present in the crude oil. It has mixture of hydrocarbons. Nearly 85% carbon will be there, having aliphatic, alicyclic, and aromatic compounds, along with a small amount of nitrogen, sulfur, and oxygen compounds. It has hydrocarbons of different molecular length, but all hydrocarbons contain carbon and hydrogen with the different compositions. So what we do in refining is we fractionate several components of crude oil into number of fractions by fractional distillation. So the process what we carry out to convert this crude oil into different fraction is fractional distillation. So what is a refinery? A refinery is the plant where this crude oil is fractionated by the application of a required pressure and temperature. So vacuum distillation will give better yield, okay, compared to other process. And the products generally obtained is gasoline, diesel, heating oil, and then jet fuel, liquefied petroleum, asphalt. These kind of several fractions are obtained, where majority of the fraction obtained is gasoline, and the second major compound is diesel. Okay. So fractional distillation is carried out continuously in a specially designed tall fractionating tower or a column made up of steel. Okay, this tower, the one tower is this one. It has several trays, with each tray having small chimney covered with loose cap. This is the chimney. Okay, this is covered with loose cap. Now, when we heat the oil and send it to the fractionating tower, what happens? The vapors move up. The vapors will slightly push up these caps. what are these called as bubble caps. Okay, so in between the gap, okay, the vapors will move upwards. Okay. What this makes is it makes the effective contact between the vapor and liquid through the column. So uh, now to attain better equilibrium, so what we need to achieve is better contact between the liquid and the vapor. So that happens because of these now bubble caps. Of course, there are several other ways of conducting fractional distillation where this is one of the method. Bubble cap columns are used. Other ways, packed column towers are also used where rashing rings. It will be having of, shapes, different shaped ceramic beads will be there, glass beads will be used. Those packing can be used. What it does is it will increase the heat transfer area and also interaction between the liquid and the vapor. Vapor is rising, liquid is coming down. Okay, so this interaction between these two will improve the efficiency of fractionation. Okay. One I said bubble cap trays. This is now packed column trays and column trays. Tray tower distillation is there. Okay, so if this is the column, these kind of trays will be arranged. Okay, so this is a tray tower column. If these packings are there, random shaped either ratchet rings or ceramic materials, and even ceramic balls can be used, glass balls can be used. Okay, so vapor goes up, liquid comes down. So contact between two phases will increase when we use this kind of material. Here also that vapor phase and liquid phase contact is there in tray tower column, bubble cap tray columns and tray tower columns also. But the effectivity of this vapor phase liquid phase contact in tray tower it is less. It is more in case of packet tower and in bubble cap columns. Okay, so this is the fractionating column providing various fractions. At the top you get uncondensed gas. Here at different the fractions having different boiling points will condense at different temperatures. You get gasoline here, okay, and naphtha, kerosene, diesel. You can look at the the boiling points mentioned over here. Okay. At the bottom, you get a very thick bitumen liquid and fuel oil. Okay. So again, the different applications are mentioned here. These are indicative applications. Now, similar several applications will be there for each fractions. So what they do is they will heat crude oil at 400 degrees centigrade in the preheater, and then this heated crude oil is sent into the fractionating column. In the lower portion, the heat will be more, and comparatively it will be cooler towards the top. But still, this is a comparative, heat, not room temperature. Okay, so you can compare here 340 degrees there, here 70 degrees there. Refinery gas is going out at somewhere room temperature. So this kind of temperature difference is there that allows the condensation of different boiling fraction of liquids to condense and can be stored, okay, taken out and stored. So highest boiling fraction condenses first and at the bottom, and lowest boiling fraction at the top. So outlets are provided on the side of the column at suitable heights to withdraw the different fractions. These are different fractions based on number of carbon atoms, and boiling points are mentioned. Different uses also have been mentioned. Okay, these are the fractions of crude oil. So when we make these fractions, then only their usage is better. You cannot use crude oil everywhere. Okay. So then after cracking also, of course, if you look at that this diagram, petrol we are obtaining here. Through this fractional distillation, whatever the petrol we are getting, it is insufficient now because the automobile industry, it has grown across the world to an extent where the fractional distillation, whatever the yield we are getting, the petrol is insufficient. Earlier, we used to use kerosene for different purposes. The demand was more. If you recall, in our time, we used kerosene stoves for cooking food. Okay, for lighting also kerosene we were using. Then the kerosene demand was more. With the development of automobile industry and electricity generation, for lighting and cooking purpose, kerosene demand went down, and the automobile industry started using more of petrol. So what happened? Demand increased, but fractional distillation is not meeting the demand of the automobile industry or the transportation requirement. Now we have to find other ways. The other ways is by cracking higher molecular weight hydrocarbons into low molecular weight hydrocarbons. That cracking process is bringing down high molecular weight hydrocarbons into lower molecular weight hydrocarbons. These methods and also synthetic methods. I mentioned synthetic gas, syngas. From that again, Fischer-Tropsch process can be used to produce artificial or synthetic. So such kind of synthetic methods and cracking process also added to the fractional distillation petrol, then we are able to meet the industry requirement for petrol. Okay. So we can define cracking as the process of decomposition of the high molecular weight hydrocarbons having high boiling point to the lower molecular weight hydrocarbons of low boiling point. So cracking can be defined as the process of decomposition of high molecular weight hydrocarbons having high boiling point to the low molecular weight hydrocarbons of low boiling point. One example we can take here is decane. Okay, it is a cetan hydrocarbon. If you crack this molecule into lower molecular weight fractions, of course, the different fractions can be obtained from decane. One example I have given here is this molecule has been broken down into pentane and pentene, N-pentane and N-pentene. So two different fractions are obtained from one molecule. It's a lengthy alkane was there. Now a small molecular weight, lower molecular weight alkane, lower molecular weight alkene is obtained by this decane. Look at the boiling point of this decane. It is 174 and 174 degrees centigrade, and pentane it is 36, pentene it is 30. So low molecular weight hydrocarbons are obtained. Okay. Cracking can be carried out by two ways. One, thermal cracking. Other is catalytic cracking. So two cracking processes can be obtained. So each one is having its own advantages and disadvantages. The best one is cracking, catalytic cracking. Let us look at how thermal cracking is carried out. Basically, this thermal cracking is carried out at higher temperature and higher pressure, where first the crude oil is the fractions which are obtained in the fractional distillation. At the bottom, uh, they are not of much use, but they can be used, made as useful product. That is into petrol. We can convert those oil fractions. Okay, the bottoms of the fractional distillation can be preheated here again to 400 degrees centigrade, and sent into the reaction chamber here. So here at somewhere the reaction is carried out somewhere around 600 to 650 degrees centigrade and a high pressure of 10 to 20 kg per centimeter square. So this is high pressure. The thermal cracking requires high temperature and high pressure. What it does is with this temperature and pressure, the high molecular weight hydrocarbons are converted into low molecular weight hydrocarbons. Again, I know if you send it into the fractional distillation column, depending on their boiling points, different fractions are condensed and collected over here. The octane value of the petrol obtained, okay, gasoline here, okay, this petrol obtained is somewhere 75 to 80. Octane value is octane number actually. Octane number is the one which determines the quality of the petrol. Okay. In the later stage, I will give the definition of this octane number. It is basically the percentage of octane, isooctane and N-heptane together, where the comparison of knocking characteristic is done between the pure octane and the mixture of N-octane and isooctane. Okay, so different fractions are taken and the ratios are measured. So octane value of petrol obtained through thermal cracking is somewhere 75 to 80. Okay. The yield obtained, it will be slightly lesser in case of catalytic cracking, and octane value obtained in thermal cracking is slightly less. So we go for catalytic cracking. So what exactly we do in catalytic cracking? We heat the lower fractions of fractional distillation. Those heavy oil, it is heated in presence of catalyst. Okay, so catalyst is, it may be aluminosilicates or zeolites. Such kind of catalyst will be used. This heavy oil in presence of catalyst, in very short time they get cracked into low molecular weight hydrocarbons. Again, in catalytic cracking, we can carry out in two ways. One is by using fixed bed, another one by using fluidized bed. Okay, catalytic cracking can be carried out by using fixed bed and fluidized bed. This is the typical fixed bed catalytic cracking process where the heavy oil portions from the fractional distillation are preheated somewhere at around 400 degrees centigrade, and here 500 to 550 degrees centigrade is maintained. In the trays, catalysts are spread. Catalyst particles are spread in the trays. Even though it looks like this, actually, it will come like this. It will come like this. Trace will be like this. So the vapors, it will go like this, and liquid, it will move in this direction. Okay. So what happens? It will make the contact between the vapor phase and liquid phase, increasing the yield of this cracking process. So the low boiling fractions, in the sense low boiling point fractions will go upwards. You get cracked gases, and send it to fractional distillation column where different fractions can be taken out. Okay. So this is the way fixed bed catalytic cracking process is carried out. There is a disadvantage with this fixed bed catalytic cracking process. After some time, what happens? The oil vapors and the smoke will get deposited onto the catalyst surface, decreasing the catalytic activity. So after some time, what happens? Whatever the oil vapors we are sending, it will go without being cracked into lower molecular weight fractions. So that problem is there. In that case, what we have to do is shut down this process, remove the tray, put new batch of catalyst particles in trays, and then again you carry out the process. So that issue is there with fixed bed catalytic cracking. So to overcome this problem, what they did is they worked with fluidized bed catalytic cracking. What exactly they do is catalyst along with the heavy oils are sent into the catalyst chamber. So this is mixed. Heavy oil and catalyst powder is mixed. It is sent in with a pressure in such a way that it is in the fluidized form. Fluidized form means it will be floating. It is neither going up in this channel nor it is coming down. So it will be in the fluidized form. So what happens in the fluidized form? There is effective contact between the catalyst particles and the oil vapors, heavy oil vapors. So within a few seconds, the heavy oil or larger molecular weight fractions get broken down into lower molecular weight hydrocarbons. So the catalyst particles become heavy and they will come down. The cracked versions are sent into the top column here. So lower molecular weight hydrocarbons will be sent and they are sent into the fractional distillation column where we get different fractions. What happens to the catalyst here? It is regenerated. So once it becomes heavier with the deposition of oil and oil and smoke, so those particle needs to be removed to activate the catalyst again. What they do is they send it into the regenerator. Here the temperature will be somewhere, you can look at 550 degrees centigrade, and the lower atmospheric lower pressure is maintained here in the this is the reactor chamber. What I showed the center one, this is the reactor's chamber, this is the regenerator. Okay. So here 550 degrees centigrade is maintained with a pressure of 1 to 2 atmospheric pressure. In the regenerator, somewhere 600 to 650 degrees centigrade is maintained. What happens? The spent catalyst, the inactivated catalyst will come down here into the regenerator. All the carbon, of course, there's one step. What we can do is a steam can be purged into the heavy particles, catalyst particles, where the oil vapors can be taken off by the steam, and then further catalyst can be sent into the regenerator. When we do this, all carbon deposited onto the catalyst particles are burnt off. Okay, they are burnt off into in the form of carbon dioxide and other gases. They will go out. Now catalyst particles become activated again. They are re-sent again back into the reactor along with the feed oil. You can send it back again here. Okay. This way catalyst can be regenerated, and this process can be continuous in nature. How much time does it take in the reactor to convert into high molecular weight hydrocarbons into lower molecular weight hydrocarbons? It is very less. Just 3-4 seconds reaction, it will get converted to lower molecular weight fraction. So fluidized bed catalytic cracking is highly efficient, and the yield is better when compared to thermal cracking, and also the octane number, I said 75 to 80 there in the thermal catalytic cracking. Here in the fluidized bed catalytic cracking, octane number is 90. Okay. And also the product quality is better where aromatics are more in this catalytic cracking. That will improve the octane number. That is what we are getting a higher octane number value here. Okay. So yield is somewhere 70% yield we are able to obtain through this fluidized catalytic cracking. See, earlier in the thermal fixed bed fixed bed catalytic cracking, you needed to remove the trace and regenerate or put the fresh batch of catalyst particle, but here it is not the case. This can be run continuously where spent catalyst is regenerated and again it is reused. here. So that advantage is there. Yield is better, octane number is better, time taken is less, lower pressure, lower temperature. Okay. Of course, we are using same list. Aluminosilicates, zeolites can be used, bentonites can be used. These are the different catalysts that can be used for catalytic cracking process. Okay. So that is the advantage of fluidized bed catalytic cracking. That is one way. The other way to obtain required quality of petrol is carry out some reactions, change the molecular structure itself. What we did is in cracking, we broke down high molecular weight hydrocarbons into low molecular weight hydrocarbons. In case of reforming, this is another way of getting quality petrol. What we do is convert straight chain hydrocarbons into branched chain, cyclic chain, aromatic hydrocarbons. What it does is it will result in the improvement of petrol quality. So the octane number can be increased. So this we call it as reformation. So reformation can be defined as conversion of straight chain hydrocarbons into branched chain, cyclic and aromatic hydrocarbons to improve the quality of petrol. This way we can define the reformation. Okay, petroleum reformation. So basically it's a structural change. Okay. One such example of reformation reaction is isomerization. Look at this. This example involves N-hexane, which is a straight chain hydrocarbon. Quality of petrol, if you measure, branched chain hydrocarbons are having better octane number compared to N-hexane. I mean straight chain hydrocarbons. So here, if you look at N-hexane, can be converted into branched chain compound and 2,2-dimethyl butane can be obtained using N-hexane. So straight chain hydrocarbon can be converted into branched chain hydrocarbon. So through isomerization reaction. So the now octane number, hence the petrol quality of these branched chain compounds are better when compared to N-hexane. So petrol quality can be improved. Another example is hydrocracking. So what they do in hydrocracking is, in presence of hydrogen, hydrocarbons are cracked. So they heat under a certain temperature and pressure. For example, N-heptane, if you take hydrogenate in presence of hydrogen, it gives propane and butane. Okay, these are low molecular weight hydrocarbons when compared to N-heptane, having better calorific value, better quality of the fuel. Okay. Similarly, decane can be hydrogenated to obtain two pentane molecules. Again, pentane molecule is having lower molecular weight when compared to decane. So hydrogenation yields two pentane molecules. The quality of calorific value is better for pentane compared to decane. So this is done through hydrocracking. Dehydrogenation reaction is another way we can carry out to improve the petrol quality. In dehydrogenation, of course, this is dehydrogenation followed by cyclization. You can look at this N-hexane, the C6 hydrocarbon. It is cyclized to become cyclohexane, and what they do is further remove hydrogen, hydrogenation. What they do, what it becomes is aromatic compound. Cyclohexane, that is cycloalkane, became aromatic compound. Aromatics are having better fuel quality, a better octane number compared to cycloalkanes or straight chain hydrocarbons. So dehydrocyclization reaction will yield better quality petrol. Another example, N-heptane can be converted into methyl cyclohexane and toluene. Okay, this is again dehydrogenation, cyclization. Both reactions are there. First cyclization is happening and dehydrogenation is also happening. Okay. Another example for dehydrocyclization reaction is N-hexane getting converted into benzene. Of course, is toluene, N-heptane into toluene, conversion into toluene. So this kind of reactions, where structural modification is brought about into the straight chain hydrocarbons to improve the quality of petrol. So to improve the quality of petrol, what we can do is one, cracking. In that, thermal cracking is possible. Catalytic cracking is possible. In case of catalytic cracking, again we can do fixed bed catalytic cracking and fluidized bed catalytic cracking. Then reformation is another possibility where structural modification for the straight chain hydrocarbons is done to obtain either branched chain or aromatics. That will improve the quality of fuel. Okay, these are different possibilities employed in petroleum industries to get the required quality of the fuel. Okay, some of the questions, butane is major component of LPG, liquefied petroleum gas. Okay, so what does LPG stands for? Liquefied or liquid petroleum gas, LPG. Okay. CnH2n is the general formula for what? CnH2n. For example, C2H2 into 2, C2H4. So it is alkene. This is alkene. Okay, so you can write olefins. Carbon percentage in crude petroleum may be approximately around 85%. So what we discussed, let's have a look at a brief summary. We discussed about how to produce metallurgical coke, which is majorly used in metallurgical industries. Coke is obtained through destructive distillation of coal. A good coke should have good strength, low moisture, medium size, then good porosity, higher calorific value is required in the metallurgical industry. Then cracking is carried out for heavy molecular weight hydrocarbons and it is broken down into lower molecular weight hydrocarbons. That will improve the quality of the fuel. For cracking of petroleum, we can employ three different methods. One, thermal cracking, where high temperature, high pressures are used. In catalytic cracking, fixed bed catalytic cracking and fluidized bed catalytic cracking is used. Among these two, fluidized bed catalytic cracking produces better quality petrol in terms of octane number, in terms of yield, lesser time it will take, and also lower pressure, lower temperatures are involved in fluidized bed catalytic cracking. Okay, so with this we will end the session.